The engineering mistake that brought down a skyscraper. Welcome back to Blueprint to Reality, the channel where engineering decisions, successes, and failures are explained from the ground up. Skyscrapers represent the peak of structural engineering. They rise hundreds of meters into the sky, resist wind, earthquakes, and massive loads. Yet sometimes one overlooked mistake is enough to bring them down. Today's video explores a powerful question. What engineering mistake can bring down an entire skyscraper? Introduction. When a skyscraper collapses or suffers major failure, it is never because of a single bolt or beam. It is usually the result of a chain reaction of engineering decisions. These failures reveal critical lessons about structural design, load transfer, material behavior, construction practices, and safety assumptions. In this video, we'll deeply analyze how skyscrapers are designed to stand, the most dangerous engineering mistake, a real-world skyscraper failure, why the mistake wasn't caught earlier, and how modern engineering prevents such disasters today. 1. How skyscrapers are designed to stand. Skyscrapers rely on a carefully balanced system of forces. Vertical load path. Every load, from the roof to the floors, must travel. Floor slabs, beams, columns, foundations, soil or rock. If this path is disrupted at any point, failure can begin. Lateral load resistance. Tall buildings face enormous forces from wind, pressure, earthquake, motion. To resist these, engineers use shear walls, braced frames, moment-resisting frames, tube and core systems. Skyscrapers are not rigid towers. They are engineered to flex safely. 2. The critical engineering mistake. Underestimating load redistribution. One of the most dangerous mistakes in skyscraper design is underestimating load redistribution after local failure. This means assuming that if one element fails, the rest will remain unaffected, ignoring progressive collapse scenarios. In reality, buildings are interconnected systems. Failure of one column or connection can overload others. This leads to a domino effect. This mistake is often invisible until it's too late. 3. Real-world case study. Ronan Point Apartment Tower. One of the most important high-rise failures occurred in London. What happened? In 1968, a gas explosion on the 18th floor of Ronan Point caused one load-bearing wall panel to fail, upper floors to collapse progressively, entire building corners to fall vertically. Why it collapsed? The structure relied on large panel construction. Panels had weak connections. Loss of a single panel caused massive load redistribution. The building was not designed to resist progressive collapse. 4. Why the mistake was not detected earlier. At the time, progressive collapse was not well understood. Design codes focused on individual member strength. System behavior was largely ignored. Other contributing factors included limited computational tools, overconfidence in prefabrication systems, cost-driven design decisions. The failure exposed a dangerous gap between theory and reality. 5. How failure spread through the skyscraper. Once the initial failure occurred, loads from upper floors had nowhere to go. Adjacent panels were overloaded. Connections failed sequentially. This caused vertical collapse, loss of structural continuity, rapid downward progression. The structure did not collapse instantly. It unraveled structurally. 6. Modern engineering solutions to prevent such failures. Today, skyscrapers are designed with failure in mind. Progressive collapse analysis. Engineers now remove columns, digitally simulate explosions or impacts, check whether the structure can bridge over missing elements. Redundancy and robustness. Modern designs include multiple load paths, stronger connections, ductile behavior instead of brittle failure. Improved codes and standards. Building codes now demand disproportionate collapse resistance, minimum tie forces, structural continuity. 7. Lessons for engineers and students. This failure taught engineers that strength alone is not enough. Connections matter as much as members. Local failures can cause global collapse. Safety must account for the unexpected. Skyscrapers must be designed not just to stand, but to survive damage. Conclusion. The engineering mistake that brings down a skyscraper is rarely dramatic. It's often an assumption that one failure won't matter. Loads will behave as expected. Extreme events are unlikely. History proves otherwise. Engineering advances not only through success, but through understanding failure deeply. If this deep analysis helped you see skyscrapers differently, like, share, and subscribe to Blueprint to Reality. Comment below. Which structural failure should we dissect next? At Blueprint to Reality, we turn engineering mistakes into engineering mastery. See you in the next video.